Hello. So last week we learned all about forces. There was a lot of content. It was a big week, but we finally learned about forces. Now, this week we're going to build on that as we learn about linear kinetics, which is not to be confused with linear kinematics that we covered in week 5. We know that kinetics means that now we're dealing with forces. In this first lecture video, I want to talk about the law of inertia, which, surprise, surprise, has to do with Newton's laws of motion. And we'll also learn about this idea of the conservation of momentum. We talked about Newton's first law of motion last week. It's commonly referred to as the law of inertia. And this law explains what happens to an object if no external forces act on it, or if the net external force, so the resultant of all the external forces, is zero. More simply, Newton's first law says that if no net external force acts on an object, then that object will not move if it wasn't moving to begin with, or it'll continue moving at a constant speed in a straight line if it was already moving. And we actually used Newton's first law of motion several times already this semester. When we analyzed projectile motions, for example, we resolved the motion of the projectile into its horizontal and its vertical components. Vertically, the velocity of the projectile was constantly changing, and it was accelerating downwards at an acceleration of 9.81 meters per second squared because of gravity. So in the vertical direction, Newton's first law does not apply because the velocity is changing. However, horizontally, the velocity of the projectile was constant and its acceleration was always zero because there was no horizontal force acting on the projectile. And this is a case where Newton's first law of motion does apply. Newton's first law of motion also applies if external forces act on an object, so long as the sum of those forces is equal to zero. So an object may continue its motion in a straight line or continue in its state of rest if the net external force acting on that object is zero. So Newton's first law can be explained mathematically as v, or velocity, is constant if the sum of the forces, so the resultant force, is equal to zero. And likewise, the sum of the forces is equal to zero if velocity is constant. Excellent. So we're talking about the law of inertia. We should probably define inertia. Inertia is defined as the property of an object to resist changes in its motion, or otherwise said, the resistance of an object to a change in its current state. So it's an object's ability to obey Newton's first law of motion. So imagine that there's this 10-kilogram dumbbell that's just sitting on a table. What happens if that table is removed from under the dumbbell? What force would you have to exert to stop the dumbbell from falling? Vertically, gravity exerts this downward force that's equal to the weight of the dumbbell, which is 98.1 newtons downwards, so negative. And your hand exerts this reaction force that's in the upwards direction against the dumbbell to stop it from falling. So according to Newton's first law, an object will stay at rest only if the net external force acting on that object is equal to zero. So that's what we're seeing here. The net force, or the sum of all the forces, that's the same thing, is equal to zero if an object is at rest. So if we break that down, the sum of the forces in this case is the reaction force from your hand plus the force of gravity, which is in the opposite direction, so a negative sign there. That's all equal to zero, which means if you isolate your reaction force, you would need to apply a force of 98.1 newtons upwards in order for this 10-kilogram dumbbell to remain at rest. Newton's first law of motion provides the basis for what we call the principle of conservation of momentum. So if we just start by defining momentum, it's the product of an object's mass and its linear velocity. So linear momentum, which we use the letter L here because we're running out of letters. It's equal to mass times linear velocity. So the faster an object moves, the greater its velocity, the more momentum it has. And likewise, the larger an object's mass, the more momentum it has. And that's just because of this relationship here, this equation. In sports and in human movements in general, most objects that we deal with have a constant mass. So if the velocity of an object is constant, then its momentum is constant as well because mass doesn't change. This means that momentum is constant if the net external force is also zero. So that's what we're showing here. Momentum, L, is constant if the sum of the forces is equal to zero. So using the conservation of momentum principle to analyze just a single object is not worthwhile. It doesn't really provide any information if the mass of that object doesn't change. But I'm teaching us what the conservation of momentum is, which means that there is some sort of value in learning it. And that value becomes apparent when we're talking about a group of objects, so not just a single object anymore. The analysis of a system of two or more objects is simplified if all the objects are considered part of one thing, which we call the system. And if the objects are considered together as one system, then the forces that these objects exert against each other, they're called internal forces, and they don't affect the motion of the whole system. Because remember that internal forces don't cause motion. And if you don't remember that, then I invite you to go back to last week's lecture content because I talked about internal and external forces last week. So only external forces will change the motion of the system. According to the conservation of momentum principle, the total momentum of a system of objects is constant if the net external force acting on the system is zero. So if I just bring back the previous equation, I can confirm what I just said here. The total momentum of a system, so L, is constant if the net external forces acting on that system is zero. If we now considered this same equation, but for all of the objects in the system, it would look like this. So for a system made up of a number of objects, the sum of the momenta, so plural for momentum, the sum of the momenta of all the objects at some initial time is equal to the sum of the momenta of the objects at some later time or some final time if there are no external forces acting on the system. So remember that this always has to be true for the law of inertia. So if I just break down this equation, because it's a long one, we know that momentum is mass times velocity, and that's all that this is showing you here. If you have two objects in your system, then the sum of the momenta initially is mass 1 times velocity 1 plus mass 2 times velocity 2. So 1 and 2 here refer to two separate objects. Those initial conditions are equal to the final conditions or the final momentum. And the conservation of momentum principle is especially useful when we're analyzing collisions. And collisions are quite common in sports when you think about it. Baseballs collide with bats, tennis balls hit rackets, soccer balls hit feet, players collide in football and rugby, etc. The outcome of these collisions can be explained with the conservation of momentum principle. So when two objects collide in a head-on collision, their combined momentum is conserved. So if we just try a simple demonstration to prove this principle here to help us visualize it, the point is to use this conservation of momentum principle to predict the post-collision movements of the objects if we know their pre-collision velocities and their mass. So if we look at this GIF or GIF, whatever it's called, on the right here, there are these 5 marbles that are all the same weight. They're the same size, they weigh the same amount. So what happens after the left marble collides with the next one? If we call this left marble marble A, just after colliding, marble A stops or barely moves. And that last marble, which we'll call marble B, it now moves in the same direction and with about the same velocity as marble A did just before the collision. So just before the collision, the total momentum of the system was the mass of marble A times its velocity. And since marble B isn't moving until the collision, it didn't contribute to the total momentum of the system. But then just after the collision, the total momentum of the system is the mass of marble B times its velocity. And momentum is conserved, right? It's the conservation of momentum principle. So when marble A collides with these middle marbles and eventually marble B, it transfers its momentum to each of these marbles, which in turn transfer their momentum to the next and the next and the next, and eventually that momentum gets transferred to marble B. So if we look at our equation for the conservation of momentum, for the marble example, ignoring the middle marbles, the equation becomes mass of marble A times pre-collision velocity of marble A plus the mass of marble B times the pre-collision velocity of marble B is equal to, right, conserved, equal to mass of marble A times post-collision velocity of marble A plus mass of marble B times post-collision velocity of marble B. Now we observed that the velocity of marble A was 0 after the collision, and that the velocity of marble B was 0 before the collision. So we can simplify our equation to something that looks like this. We just have the mass of marble A times the pre-collision velocity of marble A is equal to the mass of marble B times the post-collision velocity of marble B. But we also know that the mass of the two marbles are the same. So MA is equal to MB. We can get rid of that. And we have a very simplified equation now. The pre-collision velocity of marble A is equal to the post-collision velocity of marble B. So for head-on, perfectly elastic collisions of two objects with equal mass, the pre-collision momentum of each object is totally transferred to the other object post-collision. Okay, so that's two objects that have the same mass. What if the masses of the two colliding objects are not equal? Will momentum totally transfer from one object to the other and vice versa? As we see in this video, object 1, we'll call that the green ball, it's heavier than object 2, which is the purple ball. So after the collision, the momentum from object 1 is not completely transferred to object 2, and object 1 actually keeps moving a little bit after the collision, right? Boom, and it's still rolling. So let's bring back our conservation of momentum equation. So this equation here is not enough if we want to solve for the two unknown post-collision velocities, right? We've got two unknowns now in our equation because both objects are still moving after the collision. So we need two equations for two unknowns. And we'll talk more about this next week, but we need to know that in a perfectly elastic collision, not only is momentum conserved, but kinetic energy is also conserved. And we'll learn about kinetic energy next week. So for now, just trust me on this. Conservation of kinetic energy gives us the additional equation that we need to determine the post-collision velocities of the two objects, if it's a perfectly elastic collision, as is the case here. So these are the two equations. You can see that in each of these equations, we're isolating the post-collision velocity, either of object 1 or object 2. So there are two separate equations for each of the post-collision velocities. So that was a lot. I'm just going to recap the past few slides here. The examples of the marbles hitting each other, that was an example of a perfectly elastic collision in 2 dimensions of a moving object with a non-moving object. So if the colliding objects have equal masses, like the marbles did, then these equations apply. So the pre-collision velocity of object 1 is equal to the post-collision velocity of object 2, and vice versa. The pre-collision velocity of object 2 is equal to the post-collision velocity of object 1. That's if the objects have equal masses. Important there. If the colliding objects have different masses, then these are the conservation of momentum equations that you would apply. So, like we just saw, the 2 marbles still have post-collision velocities, so we need 2 equations to be able to find those 2 unknowns. Okay, that's it for this first lecture video. Stay tuned because we have some more conservation of momentum stuff to learn about.